and enjoy Passport to the Universe.
This is Tom Hanks. What you are about to see is not an artist's fantasy, but a three-dimensional map of the real universe, carefully calculated and drawn from the best astronomical observations and data. Before we begin our journey, I need to run through a pre-flight checklist. Planet program. Solar system orbits, planets, moons, and rings. Check. Star program. Local star positions, colors, and magnitudes. Check. Galaxy program. Milky Way and galactic coordinates. Gas and dust nebulas. Check. Universe program. Local group of galaxies. Virgo supercluster. Check. Late-breaking astronomical images. Check. Okay, we're ready to roll. In the time before electricity, in a world lit only by fire, this was the sky that everyone knew. Back then, on a clear, moonless night, it was always dark enough to see the faint band of the Milky Way arcing across the sky. For 1,000 generations, our ancestors looked at the night sky and wondered what it was. The sky looked like the inside of an enormous bowl, slowly turning around an Earth believed to be at its center. The stars were like tiny points of light stuck to the inside of the bowl and not so very far away. The ancient sky seemed two-dimensional. Our ancestors imagined that the stars formed pictures in the sky. They named these constellations after mythical creatures and heroes. But what were the stars, really? What was the Milky Way? For that matter, what was the Earth? And where was it? We had no way to know until we devised the methods and tools of science. Because our eyes are very small and the stars are far away, at best we can only see a few thousand of them, even on the darkest night. But for every star we can see with the unaided eye, the night hides 50 million others in our Milky Way galaxy alone. Using telescopes, we discovered that the sky has a third dimension, depth, and that the universe is far grander than anyone could have imagined. During the last 400 years, in a series of astonishing discoveries, we filled out our cosmic address. We learned that, far from being the center of the universe, the Earth is actually but one of the planets, moving in orbit around the Sun. Our Sun, in turn, is just an ordinary star. It is one of over 100 billion stars in our Milky Way galaxy. And our Milky Way galaxy is one of several thousand galaxies in the Virgo supercluster. Finally, this vast supercluster of galaxies is but a tiny part of the observable universe. Using telescopes and the laws of physics, we are mapping the universe in 3 dimensions. And once you have a map, you can know where you are and where you're going. That's Mars. After the Earth, the next planet out from the Sun. The gas giant planet Jupiter is heavier than all the other planets put together. Its great red spot is a storm that has raged for centuries. Each of its big moons is an unexplored world in its own right. One of them, Io, has volcanic eruptions at all times. Another, Europa, has a deep ocean of water hidden beneath an icy crust. The planet Saturn has hundreds of thin rings made of countless orbiting snowballs. With our computer on interplanetary drive, we've come this far in only a minute. Our fastest spacecraft actually take years. We've come a long way. Can you find the Earth? It's so small, we can hardly see it from here. It's that one, the pale blue dot. That's home. Everyone you ever knew or ever heard of came from that tiny spot. The planets of the solar system are huddled close to the sun, like campers around a fire in a vast, cold, and dark plain. From out here, it's obvious that our mighty sun is just another star. But the familiar constellations still look the same, because even at this distance from Earth, the stars are still enormously far away. Connect the dots, and there's Orion, the hunter. The three stars in the belt make this constellation easy to find in the winter sky. Below Orion's belt, you can see a faint, wispy cloud. It doesn't look like much because it's so far away, but just wait. The stars are millions of times farther away than the planets. To move among the stars, we'll have to shift to the interstellar drive. As we move out into our galaxy, the old two-dimensional patterns vanish because the starry sky is three-dimensional. We're heading for the Orion Nebula, about 1,500 light years from Earth. The Orion Nebula is a recycling center for the stars of the Milky Way, a vast interstellar cloud of gas and dust, a place where stars are born. We're entering a virtual landscape of the nebula, assembled from observations with the Hubble Space Telescope. No one has ever seen the Orion Nebula like this before. The brightest stars illuminate the surface of the nebula from which they are born. Our solar system was made in a place like this, a stellar nursery. That was a long time ago, of course, nearly 5 billion years. But it must have looked pretty much the same. Each of these teardrop-shaped clouds is a blanket of gas and dust swaddling a newborn star, and perhaps a family of growing planets. And what does all this have to do with us? Take a deep breath. No, I'm serious. Really, everybody, do it. Every atom of oxygen you just inhaled was made deep inside a star. The carbon in our muscles, the calcium in our bones, the iron in our blood, in fact, all the heavy elements were cooked inside the hearts of stars. As Carl Sagan said, we are star stuff.
Take just a few minutes now to explore a little bit some of the things that astronomers have been finding in some of those clouds of gas and dust, like we just saw, where new planets are forming around new stars. Now, until very recently, we could only guess at how other star systems formed based on what we saw in our solar system alone. But today, astronomers are able to see stars up close, and not only the stars, but sometimes the planets forming around those stars too. And these observations allow astronomers to make models like this one. We're looking here at a model of a newly formed star, which we're seeing in the center there, that we're kind of zooming away from. Oops, we just passed through the gas jet there. We're seeing this large disk of gas and dust swirling around the newborn star, and there are these jets of gas that are coming out of the star as well. You can kind of think of those as the first baby star burps of the newborn star. And some of this disk material, it'll fall in towards the center, it'll become part of that new star, but a lot of what we're looking at here are the building blocks for planets. And once upon a time, we thought that all star systems, all planets, even ones outside of our solar system, must have formed very much the same way that our solar system did, looking very similar to this, with resulting systems and planets that would all be fairly similar. However, new generations of telescopes within just the last few years have begun to reveal this process in an amazing amount of detail. And as we did start to discover these locations in detail, we were kind of surprised to find that there's actually quite a lot of variation in how these systems can look as they're forming, and in the resulting planets and systems that we see too. These are just a few examples of some of these disks of gas and dust around newborn stars, and in several of these, let me point out for you, several of these you can even see, let's go the other way. In several of these you can even see these dark lanes where planets are forming inside of the disks. And these are some of the most high-resolution images that we have of some of these forming systems so far. These ones are all from the ALMA telescope array, which is down in Chile. And even in just these couple dozen examples, you can see quite a lot of variation. So, as astronomers started to find more and more of these systems forming and already formed, people began to wonder, wait, is our solar system not the rule? Are we an exception? Is there a rule, and if so, what is it? And that's one of the things that astronomers are still trying to figure out. Is there a rule? Is there a way to predict what these other star systems will look like based on a variety of different factors? And so far, we have found many of these locations. Every single one of these blue markers here is showing us the location of a star that has at least one exoplanet, what we call a planet outside of our solar system. And we've only been discovering exoplanets since the mid-1990s, but we're already up to over 4,000 confirmed exoplanets, and we're finding more every single year. But there are a lot of different factors that can play into how these exoplanets end up looking. Things like, how big was that disk of gas and dust? What was its temperature? What was its density? What was it made of? How was it moving? What kind of star formed? What else was around? There's a ton of things that can change that. But we can focus in on particular factors, make models based on those factors, move those models around to try to predict what kinds of exoplanets we expect to see based on certain things. So that's what we're going to do right now. We're going to focus in on just one factor. How big was a disk of gas and dust when one of these systems formed, and how does that change the types of exoplanets we expect to find? And we'll start out this exploration by first taking a little bit of a closer look at our solar system. Now, when we look at the planets in our solar system, there's a few distinct sections. There's a few different types of planets that we see here. For example, if we look at the planets closest to the sun, this is where we find the smaller, rocky, terrestrial planets. Terrestrial meaning like Earth, and rocky meaning they all have solid surfaces. In theory, if you wanted to go and walk around on any of these planets, you could do that because they do have solid surfaces. And these four are Mercury, Venus, Earth, and Mars. And they're all relatively small, they're all relatively close to the sun. But if we move a bit farther out, if we get past the asteroid belt in our solar system, we get to a second section of planets here that's quite a bit different. This is where we find the large gas giants, Jupiter and Saturn. Now these two, they do not have solid surfaces. If you wanted to walk around on them, that wouldn't work out too well. You would sink right into them because they're made mostly of hydrogen and helium gas. And then farther out still, we find the ice giants, Uranus and Neptune, which are usually separated out from the gas giants because you can see they're substantially smaller, but also they have a little bit more of a slushy consistency compared to the gassy consistency of Jupiter and Saturn. And like I mentioned before, for a long time, we thought this must always be how it is. Rocky planets close into a star, gas giant planets farther out, ice giants farther out than that. But we have found a lot of exoplanet systems that just don't really seem to fit that trend very well at all. But if we do make models that are based on how big a disk of gas and dust was, and we think that our system started out as kind of a medium-sized disk of gas and dust, this is the type of model that we come up with. We expect to find smaller, rocky planets in the red area right in the center, close to the star. We expect to find large gas giant planets farther out in this yellow area, and we expect to find ice giants in the blue area farthest out. Now, if you look carefully, you can see this model doesn't fit perfectly. Jupiter does go inside the red a little bit, Uranus goes inside the yellow a little bit, but for the most part, this fits really well with what we do in fact find in our solar system. But what if we started out with something different? What if the only thing that was different was we started out with a bigger disk of gas and dust? What will we see then? Well, then we would expect something more along the lines of this. A very, very tiny area close to the star where you might find a smaller rocky planet, a gigantic area going all the way out to Neptune where you might find a large gas giant, and an area much farther out where you might find an ice giant. In this model, this is based on a variety of different observations, but I do have one specific example that fits this really well, the Kepler-9 system. Now I'm putting our model of Kepler-9 on top of our solar system so we can compare the two easily. And Kepler-9 has a star that is really, really similar to the sun. Actually, we might be upside down. No, this works, okay. It has a star that is really, really similar to the sun, which we're seeing right over here. It's almost exactly the same size, about the same temperature and everything. But other than that, this system is pretty different. For one thing, we have found only 3 exoplanets in Kepler-9, one right over here, one right over here, and one right here. But these farther two, these are both gas giant planets, but they orbit roughly where Mars and Earth would be in our solar system. And there is a rocky planet here, but it is really, really close into the star, even closer than Mercury is to our sun. So that's one example of a system we think started out probably a lot bigger than our solar system. What about a lot smaller? Well, I do have a good example of this too, but we have to flip around and zoom in really close to see it. Because this system, TRAPPIST-1, the entire thing would easily fit inside of Mercury's orbit. It's incredibly small. But TRAPPIST-1 was a really exciting find when astronomers found it just a few years ago because it has not just 1, not just 2, not just 3, but 7 exoplanets that are going around a very small, red, dim star. So, roughly the same amount of planets that we have here. And not only that, but we're pretty sure that all 7 of those planets are rocky planets and that they're all roughly the same size as the Earth, ranging from about half to about 2 times the size of the Earth. So this is a place we would really love to know more about. So far, with the telescopes and the technology we have right now, we can't get a ton more details about most of these exoplanets. So far, we can't really see atmospheres too well. We can't really see like what exactly the conditions might be like on these exoplanets. So hopefully in the coming years, we'll get even better telescopes that can tell us a bit more details. But in general, when we're talking about systems that started out a lot smaller than our solar system, this is what we expect to find. We expect to find smaller, rocky planets in a pretty large area around the star, going out to about Saturn in our solar system. You may notice we're missing yellow. You would not expect to find a Jupiter or a Saturn-sized planet in a system like this, just not enough material to make one, basically. And there's this area of blue with red dots where we might find a type of planet that we haven't found in our solar system. A super-Earth, a planet that's bigger than us, but not quite on the order of a Uranus or a Neptune, and has more of a mixture of ice and rock. And again, this is pretty much just based on one thing, just how big was a disk of gas and dust when one of these systems formed. And astronomers are constantly scanning the skies, trying to find more and more of these exoplanet systems, trying to just kind of fill in our catalog of all the different possibilities that may be out there. So make sure to keep your eyes peeled in the coming years, see what else we may learn about any of these locations or new ones we can't even imagine right now. But in the meantime, let's head back to the last half of our show. We're going to take off where we left off, flying amongst the stars, and we're going to take a look at what we think our galaxy looks like from the outside.
Stars are born in batches, with dozens in every litter. The sibling stars of our sun are now spread throughout the spiral arms of the Milky Way galaxy. As we leave our galaxy, the individual stars appear to blend together. Our Milky Way is really a vast spiral galaxy, a congregation of hundreds of billions of suns. But you have to get out here, outside the galaxy, to see the whole thing. We've never had this view before. Remember back on Earth, where we could only see a few thousand stars? Well, all of them lie within that tiny part of the galaxy. Every one of those spots isn't a star, but a whole galaxy with billions of stars. We're now in intergalactic drive, moving through virtual space at millions of light years per second. That's the Andromeda Galaxy, our nearest neighboring spiral galaxy. It's the largest member of the so-called Local Group, a collection of a few dozen galaxies. Our Local Group is a small part of the Virgo supercluster, a vast gathering of several thousand galaxies. From out here, it's hard to spot our own Milky Way galaxy. Well, it's that one. That's home. Our supercluster of galaxies is only a tiny part of the observable universe. On the largest scale we can see, the superclusters form the knots of a tangled network, or web. The brightest knots are entire superclusters of thousands of galaxies, with each galaxy containing billions of suns. This is the last line of our cosmic address. For now, anyway. We may be just little guys, living on a speck of dust. But we don't think small. We managed to figure this much out. And we're still figuring. There are about 100 billion galaxies in the universe we can see, but there are parts we can't see. And who knows? It may be that all this, the entire observable universe, is one tiny bubble in an infinite universe hidden beyond our cosmic horizon. It's time to be heading back. Let's see if we can find a black hole around here somewhere. Black holes are places where gravity is so strong that not even light can get out. Some theories imagine that they provide shortcuts to connect distant parts of the universe. No one knows what it might look like inside, so we're free to imagine it. Well, we got off in the right neighborhood. Welcome home, fellow citizens of the cosmos. Your passports are now good everywhere in the universe. Among the planets of our solar system, the stars of our Milky Way galaxy, the other galaxies of our supercluster, and on out to our cosmic horizon. Next time you look up at the clear night sky, remember, you, me, and everybody, we are star stuff. We are in the universe, and the universe is in us. In the deepest sense, we are citizens of the cosmos.